The aim of this project was to design, build and test a simple wing structure for an aircraft optimized for minimum mass under spanwise bending and torsion constraints. There are 4 main stages of design engineering that are followed, which will be discussed in this video. At this stage, engineers brainstorm as many solutions as possible to the task and note them down using pencil and paper. They research similar challenges others have faced and existing solutions to incorporate them, or if they require, new concepts. In the wing design, we brainstormed ways to reduce weight, leading to the idea of creating holes, circular, oval and square. We also researched wing spar cross-sections to withstand the load, as the spar is assumed to carry all the load. We selected a hollow rectangle, circle and I-beam for analysis in the preliminary stage. At this stage, engineers use software like Excel to assess the performance of the design concepts by varying key inputs, analyzing the resulting data and afterwards selecting the optimal design. If no positive results are found, the process is repeated. Having restricted material choices limits the choice of functionality, because materials vary in functionality. For the wing design, we used Excel spreadsheets to analyze the effect of design inputs on parameters such as bending moments, geometry, and torsional compliance. After analysis, we determined that a hollow rectangular beam was best for withstanding both bending and torsion. We also found circular holes to be most efficient for the spar, as they reduced the weight and were reasonably sturdy. Using the Euler-Bernoulli beam theory, we can calculate the maximum direct stress that can act on a spar. And for a beam not to break, the maximum direct stress should not exceed the ultimate direct stress of the material. We were able to input this as a logic test in Excel to see if our design inputs failed or passed. Analyzing the spar as a cantilever beam with a point load at the tip deflection was calculated using. After selecting the optimal design concept, the next step is to create a version of the design, often starting with a scaled model. Most engineering designs involve multiple parts, so a 3D model helps visualize the final assembly. CAD tools like SolidWorks allow for simulations to identify design flaws and refine the design before moving to manufacturing. At this stage, real-world conditions, which might have been ignored in the previous stage to simplify analysis, must be considered. For the wing design, the spar was made from laser-cut foam board and assembled with hot glue, whose weight was ignored during analysis, while a sleeve to hold it in place when clamped was designed in SolidWorks and 3D printed. At this stage, physical experiments are done to test if the design model meets the requirements under practical conditions. If it meets the design requirements, the design model will be sent to the manufacturing process, or minor refinements might be done beforehand. Otherwise, engineers must restart the design process while considering the failure of the previous design concept in the new conceptual stage. In our experiments, we tested spar deflection by clamping one end and gradually adding weights at the other end until reaching a load factor of 2.5. The maximum deflection was 27.6 millimeters, indicating the spar could handle this load. Torsion was tested by suspending weights from a 30 centimeters ruler attached to the spar. An angle of 5 degrees was measured using a phone, failing the torsion test. When performing the lab test on torsion, it was found that the spar turned through a larger angle than estimated on the spreadsheet. This could be due to an incorrect experimental setup, leading to an inaccurate answer. It could also be due to the instability of tape and glue. In summary, by using Excel analysis and SolidWorks modeling tools for testing and continuous design and modification, we finally selected the optimal design solution. Meanwhile, certain accuracy errors need to be further avoided.